Somewhere in the silent depths of space, beyond what the human eye can easily comprehend, a powerful and invisible force has just stirred. Not a sound in the traditional sense, but a disturbance so strong that it rippled across millions of kilometers, reaching all the way to Earth. Scientists call it a radio shockwave, a burst of electromagnetic energy tied to one of the most intense magnetic environments in our solar system. This phenomenon originates from the enormous magnetic field surrounding the largest planet in our cosmic neighborhood. It is not a calm or gentle field. It is violent, fast-moving, and constantly interacting with charged particles trapped in space. When these interactions intensify, they produce powerful radio emissions, almost like a natural cosmic broadcast that carries across the solar system. Recently, something unusual happened. A sudden surge of activity within this magnetic system created a shockwave strong enough to disturb space weather far beyond its origin. This was not just a distant event confined to deep space. Instruments on Earth detected subtle but real changes in radio signals, confirming that the energy had traveled across the void and brushed against our planet's protective magnetic shield. What makes this so fascinating is not only the distance it traveled, but the message it carries. Space is not empty or quiet. It is alive with electromagnetic interactions, constantly shifting and communicating in ways we are only beginning to understand. These radio bursts act like cosmic fingerprints, revealing hidden dynamics of planetary environments that cannot be seen with light alone. For scientists, such events are more than just curiosity. They are clues about how magnetic fields behave, how planets interact with space weather, and how energetic particles move across vast distances. Each signal helps refine our understanding of the solar system as a connected, dynamic system rather than isolated worlds drifting in silence. And while Earth remains safely shielded by its own magnetic field, events like this remind us that we are not separated from the universe. We are part of its constant conversation, a conversation written not in words, but in waves of energy traveling through the fabric of space. A powerful radio shockwave originated from intense magnetic activity in space and was detected on Earth. A powerful radio shockwave has been detected traveling through space after emerging from an extreme burst of magnetic activity, and its influence was strong enough to be recorded far beyond its point of origin, even reaching Earth through subtle disturbances in space-based instruments. This event is not something that can be seen with ordinary light or felt in a physical way, but it is carried through electromagnetic waves that move across vast cosmic distances at incredible speed. These waves are part of a natural process where intense magnetic environments interact with charged particles, releasing energy in the form of radio emissions that spread outward like ripples in an invisible ocean. What makes this occurrence so remarkable is the strength and scale of the energy involved. The region where this shockwave began is known for having one of the most powerful and dynamic magnetic systems in the solar system. Within this environment, charged particles are constantly trapped, accelerated, and colliding under the influence of magnetic forces. When conditions become especially active, these particles release bursts of energy that can grow into massive radio waves capable of traveling millions of kilometers through space without losing their identity. As this particular wave moved outward, it did not simply fade into nothing. Instead, it carried enough energy to slightly disturb the space environment surrounding Earth. Sensitive instruments detected changes in radio signals, showing that the wave had interacted with Earth's magnetic shield. Although it posed no danger, its presence was a clear reminder that space is filled with constant activity, even in regions that appear empty and quiet. This kind of event also highlights how interconnected the solar system truly is. A disturbance originating from one distant region can still influence conditions near Earth, showing that planets and magnetic fields are part of a larger dynamic system. Scientists study these shockwaves carefully because they reveal important details about how energy moves through space, how magnetic fields behave under pressure, and how cosmic environments respond to sudden bursts of activity. The source is linked to a strong and highly active planetary magnetic field interacting with charged particles. As the radio shockwave continued its journey through space, it revealed something far more complex than a simple burst of energy. It demonstrated how deeply interconnected and constantly active the solar system truly is, even in regions that appear empty to the human eye. This wave did not move as a random disturbance. It followed the structure of magnetic fields and plasma currents that stretch across vast distances, shaping the way energy travels between planetary bodies. The origin of this event lies in a highly charged magnetic environment where enormous forces constantly interact. Within such regions, charged particles are trapped in spiraling motion, gaining energy until a sudden shift in conditions releases them in powerful bursts. These bursts create radio waves that behave like natural signals, carrying information about their source across space. When the recent shockwave formed, it was not just a single explosion, but a chain reaction of magnetic instability that amplified itself as it expanded outward. As it traveled, the wave passed through different layers of space weather, each with its own density, pressure, and magnetic structure. Instead of breaking apart, it adapted and continued forward, carrying a strong enough signature to be detected even at Earth's distance. When it reached the near-Earth environment, it interacted with our planet's protective magnetic field, causing small but measurable disturbances in radio frequencies and charged particle behavior. These interactions are extremely important for scientists because they help reveal how energy moves through space that cannot be directly observed. Every disturbance acts like a message encoded in waves, showing how distant cosmic regions behave under extreme conditions. By studying such events, researchers can better understand solar system dynamics, predict space weather, and protect satellites and communication systems that depend on stable electromagnetic conditions. In a broader sense, this event highlights that space is not silent or static. It is a living system of constant motion, where invisible forces communicate across unimaginable distances. Each shockwave, burst, or fluctuation becomes part of a larger cosmic pattern, reminding us that Earth exists within a vast and energetic network that never truly stops moving or changing. This interaction produces strong radio emissions that travel across the solar system as electromagnetic waves. When the radio shockwave finally reached the vicinity of Earth, it did not arrive as a dramatic impact or visible phenomenon, but rather as a subtle disturbance woven into the invisible fabric of space. Instruments designed to monitor cosmic activity recorded small fluctuations in radio frequencies and charged particle behavior, indicating that a wave of significant energy had passed through the region. Although the planet's magnetic field acted as a strong protective barrier, it still responded slightly to the passing energy, revealing just how sensitive Earth's space environment is to distant cosmic events. This interaction highlighted the role of Earth's magnetosphere as both a shield and a dynamic system. It constantly deflects harmful solar and cosmic radiation, but it also responds to changes in external magnetic pressure. When a strong radio wave passes through, it can compress or stretch the magnetosphere slightly, creating detectable variations in signal patterns used by satellites and ground-based instruments. These variations are not dangerous in this case, but they serve as valuable data points for understanding how space weather behaves. The shockwave itself carried encoded information about its origin, preserved in its frequency patterns and energy structure. By analyzing these signals, scientists can trace back the conditions that produced the event, including magnetic field strength, particle density, and the level of instability in the source region. This allows researchers to build a clearer picture of how such extreme environments function and why they sometimes release sudden bursts of energy. What makes this particularly important is the way it demonstrates the chain reaction nature of space. A disturbance that begins in a distant magnetic environment can travel across millions of kilometers, passing through multiple cosmic regions before finally interacting with Earth. Along the way, it remains structured enough to carry information, almost like a message written in waves rather than words. Events like this reinforce the idea that space is not empty or passive. It is an active, responsive system where energy is constantly moving, reshaping, and interacting. Even the smallest disturbances can reveal large-scale patterns, helping scientists understand the hidden connections that bind the solar system together in a continuous flow of electromagnetic activity. The recent burst was powerful enough to slightly disturb Earth's space weather and be measured by scientific instruments. The arrival of the radio shockwave near Earth offered scientists a rare opportunity to observe how distant magnetic activity can influence local space conditions without causing any direct physical disruption. Instead of a visible impact, The event manifested as a subtle but measurable shift in the behavior of charged particles and radio signals passing through Earth's upper atmosphere. These small variations may seem insignificant at first glance, but they carry deep scientific meaning, revealing how energy from distant regions can still shape conditions around our planet. One of the most important aspects of this phenomenon is how it interacts with Earth's ionosphere, a layer of the atmosphere filled with charged particles. When a strong radio wave passes through, it can slightly alter the density and movement of these particles, leading to temporary changes in signal transmission. This is why sensitive monitoring systems are able to detect even distant cosmic events. The ionosphere acts like a natural receiver, constantly responding to energy coming from space and reflecting those changes back in measurable ways. At the same time, satellites orbiting Earth provide additional data by recording fluctuations in electromagnetic activity. These instruments help build a real-time picture of how space weather is influenced by external forces. In this case, the passing shockwave created minor disturbances that helped confirm the strength and reach of the original event. Without these modern technologies, such subtle interactions would remain completely invisible. What makes this event scientifically valuable is not its intensity, but its distance and clarity. The fact that a wave generated so far away can still be identified at Earth shows how efficiently electromagnetic energy travels through space. It also demonstrates how structured these waves remain over vast distances, preserving information about their origin long after they were created. This kind of observation helps improve predictive models for space weather, which is increasingly important in a world dependent on satellites, communication systems, and navigation technologies. By studying how distant magnetic disturbances interact with Earth, scientists can better anticipate potential impacts on technology and infrastructure. Ultimately, this event reinforces a powerful idea. Earth is not isolated in space. It is continuously influenced by a network of invisible forces that connect planets, fields, and particles across the solar system in an ongoing dynamic exchange of energy. Such events help scientists better understand space weather, magnetic fields, and the hidden connections between planets in the solar system. Beyond the immediate scientific measurements, this radio shockwave carries a deeper significance for how humanity understands the structure and behavior of the universe. It demonstrates that space is not a silent void but a constantly active environment where energy, matter, and magnetic fields interact in complex and often unpredictable ways. Every burst of activity, no matter how distant, contributes to a larger cosmic system that is still being mapped and understood. As the wave slowly dissipated after passing Earth's vicinity, its effects gradually faded from detection, but the data it left behind continues to be analyzed. Scientists examine variations in frequency, intensity, and timing to reconstruct the journey of the wave from its origin point to its final interaction with Earth. This process is similar to tracing ripples across a vast ocean, where each distortion in the surface tells a story about the force that created it. One of the most fascinating outcomes of studying such events is the realization that magnetic environments act like communication channels across space. They do not transmit messages in a traditional sense, but they carry energy patterns that reveal the state of distant regions. In this way, the universe becomes readable through its electromagnetic signals, allowing researchers to decode conditions that would otherwise remain completely hidden. This particular event also highlights the importance of continuous monitoring systems placed both on Earth and in orbit. Without these instruments, such subtle interactions would pass unnoticed, and valuable insights into cosmic behavior would be lost. The ability to detect and analyze distant magnetic disturbances has become essential for understanding space weather, protecting technological infrastructure, and preparing for future high-energy events. In a broader perspective, this shockwave serves as a reminder of Earth's position within a much larger and constantly changing system. Our planet is not isolated but deeply embedded in a field of energetic interactions that stretch across the solar system. Each event, whether large or small, contributes to an ongoing exchange of information carried by invisible forces. In the end, the passing wave is not just a scientific observation but a glimpse into the hidden rhythm of the universe, where motion, energy, and magnetic influence are always at work, shaping reality far beyond what human senses can directly perceive.